cloud. Okay, I did it. Okay, good.
Mm-hmm.
So welcome, David. Welcome back to this for this second lecture. And so please, you have an hour and a half again, and still with some flexibility.
Right. Thank you very much.
Thank you.
Very good. So today we have a quite dense program. So I want to discuss essentially powerful Krylov space methods to get eigenstates and eigenvalues of large sparse matrices. We discussed already yesterday that we can devise algorithms which use only matrix vector products. The power algorithm was one example that we discussed, and now we will refine this to become a so-called projection method using the Rayleigh-Ritz procedure, which I will explain, and which will eventually culminate in combination with Krylov subspaces to be either the Arnoldi or Lanczos algorithm. I think I'll just discuss the more general Arnoldi case and just tell you where the loops end in the Lanczos case, which simplifies a little bit. And then the next thing I want to discuss are spectral transforms, because as we already discussed yesterday, direct power method and Krylov space methods give you only access to the edge of the spectrum, but for MBL studies, we are interested for this in the center of the spectrum, so we need to massage the spectrum somewhat. I will briefly mention matrix-free techniques, because it turns out that you don't actually need a sparse matrix. The only thing you need is to calculate the matrix vector product, and you can do this in some cases without even having the matrix. And then in the end, I want to discuss time evolution, because you can also use Krylov subspace methods for studying the time evolution of wave functions, many body wave functions, very efficiently, and this is a very interesting technique. The Krylov space in that case is very different because it is not spanned by some trial vector. It is rather spanned by the initial state, and this is a crucial change. All right, so I already wrote some things here so that we can move on rather quickly. So what we discussed with the power method was that if you apply the Hamiltonian many times on any trial wave function, then it turns out that you filter the wave function which overlap with the eigenvector, which has the largest modulus of the eigenvalue. And the space that we obtain during the power iteration is called the so-called Krylov space. So what this is if you remember, in the power iteration, we first start with psi0, that's the starting vector, and then we apply h. So then this means we get h times psi0. And then we apply h again, so this means we get in basically h squared times psi0, and so on. So if we keep all these vectors, then we get vectors which you can see here. This is psi0, this is h times psi0, h squared times psi0, up to some power h to the power m-1 times psi0. And if we keep all of them, then they span a subspace of our Hilbert space, which is called the m-dimensional Krylov space. I will use here the symbol calligraphic k with index m, so that's the dimension of the Krylov space. And crucially, this Krylov space is defined by the Hamiltonian and by a vector, which is our trial or initial wave function that we use in the algorithm. So this is psi0. We have to know these two things and the dimension, and this then defines the Krylov space. And the interesting is from what we discussed yesterday for the power iteration, that if we go to large enough m, then this subspace will contain components which have a large overlap with eigenvectors from the edge of the spectrum. And this means that the Krylov space for large enough M will contain the interesting eigenspace, which is at the edge of the spectrum and spanned by some eigenvectors at the edge. And now we want to move forward from these observations and try to understand how we can use this knowledge and use this constructive way of constructing the Krylov space to extract really exact eigenpairs of the Hamiltonian for large sparse matrices. So we have the Krylov space, and the second thing that I want to show you here, and I want you to figure out some of the details in the tutorial. I'll send around some material today so that you can prepare a little bit. So I will tell you only part of the story, and I want you to figure out more of this. But the central procedure that is a component of the Lanczos algorithm is called the Rayleigh-Ritz procedure, and I'll tell you how this works. And the task for the tutorial is to figure out why this works. All right, so the way and the Rayleigh-Ritz procedure works is we start from the Krylov space spanned generated by the Hamiltonian and some initial state, which as we've discussed in the power iteration can be a random vector. And then the first thing is we create an orthonormal basis of the Krylov space. So this means we generate M vectors which are orthogonal and normalized, and this will give us this matrix V. And now the Rayleigh-Ritz procedure is called a projection method, because what we do is we project the Hamiltonian into the subspace spanned by these vectors, so into the Krylov space, and this gives us the so-called Rayleigh quotient matrix. So R is a matrix of dimension M by M, and now V is a matrix of dimension D by M, and the Hamiltonian is of course a matrix D. V dagger is then consequently M by D. So if we multiply the Hamiltonian onto all vectors of our orthonormal basis of the Krylov space, and then take the inner product with all other vectors, we get this smaller matrix R. This is the central component, and this is really the projection of the Hamiltonian into the Krylov space. And then we just calculate the eigenpairs of R, which is of course a much simpler problem because M is much smaller than the dimension of the Hilbert space, right? So M is much smaller than B. And these eigenpairs are called Ritz pairs. So we really solve this small M by M eigenvalue problem. And then we can look at the Ritz values, lambda I, which have a relation to the eigenvalues of the Hamiltonian. So lambda I is actually an approximate eigenvalue of the Hamiltonian. Of H. And the Ritz vectors Wi are representations of approximate eigenvectors in the Krylov basis. So in order to go back to our original computational basis, we can generate the corresponding vector xi by just V, which remember is a rectangular matrix D by M. And now the statement is that if the Krylov space is big enough, some of these Ritz pairs will actually converge to be very good approximations for eigenpairs of the Hamiltonian. And the Ritz pairs which converge first in terms of M, which is the dimension of the Krylov space, are those with the largest modulus of the eigenvalue. So in particular, the largest and the smallest, so the edges of the spectrum will converge quite quickly in terms of M. And we can check the quality of the obtained approximate eigenvectors and eigenvalues by looking at the residuals. So this is called residual, which is nothing but h times the vector minus eigenvalue times the vector. And if this converges and gives, and the Ritz pair is a good approximation of the eigenpair, then the residual will be very small. And now we can repeat this procedure and just increase the size of our Krylov space, and we will get a convergence. So roughly speaking, and this will be also explicitly done numerically in the tutorial, if we plot the dimension of the Krylov space and we plot the lambda i's obtained by the Ritz pairs, then we get something like maybe this, where this is the largest eigenvalue in the spectrum, the smallest eigenvalue in the spectrum, and then you will get maybe more. So you get some convergence of the edge eigenvalues in the spectrum. So this is very nice. And this is the central idea of the Arnoldi and Lanczos algorithm. As I said, in the exercise, I would like you to figure out that the procedure is exact if you are in an exact eigenspace of the Hamiltonian. So if you have some random basis, orthonormal basis of an eigenspace of the Hamiltonian, you can explicitly show that you get the exact eigenpairs of the Hamiltonian with the Rayleigh-Ritz procedure. So this means if you have a large component of an eigenspace in your Krylov space, then this is guaranteed to work. And the second thing I would like you to play with is this convergence of eigenpairs in terms of the size of the Krylov space numerically. And you'll get a Jupyter notebook to play with this. All right, so this is just the general idea. And now the essence of the Arnoldi and Lanczos algorithms is to make this numerically efficient. Because if you think about the procedure as it is written here, you realize that it's very inefficient, because each time you generate one more vector in your Krylov space, you have to create a new orthonormal basis. And this is, of course, expensive. If you want to, you just increase the set and you create a new orthonormal basis, this is not very optimal. So the way the Arnoldi and Lanczos algorithms are designed is such that you have an efficient implementation of this procedure. But the idea is really you create an on-the-fly, an orthonormal basis of the Krylov space, project, and at the same time a projected version of the Hamiltonian Krylov space. And then you have to diagonalize this projected part of the Hamiltonian and find the Ritz pairs, which can be transformed back to the full basis. Very good. So now we will discuss essentially the Arnoldi algorithm, and as I said, the Lanczos algorithm is the special case for Hermitian matrices. Arnoldi. And then Lanczos. And these date back to two papers by Arnoldi. Well, Lanczos was the first, so let me write on that Lanczos. And that's 1950, and Arnoldi 1951. And maybe I should give you a reference. So there's a very nice paper, book by Youssef Saad entitled Numerical Methods for Large Eigenvalue Problems, where you can find all the details for large eigenvalue problems.
We have a question by Lorenzo.
Yes, please.
Hi, I was wondering, the basis over which we construct the Krylov subspace is not an orthonormal one, right?
Well, if you create just the Krylov space vectors by applying the Hamiltonian, this is not orthonormal. Yes.
But so in general, when we work out all the other steps, is it useful to search first for an orthonormal basis, or?
Yeah. So this is crucial. Okay. So in what I'm showing you, automatically an orthonormal basis is generated using modified Gram-Schmidt on the fly. Okay. We'll go through this in detail now.
Okay, thank you.
Another question by Robin Schaffer.
Yeah, Robin, go ahead.
Hi, David.
Hi.
How large do I have to choose M to get the ground state?
Well, until you converge. So you monitor a convergence, and it depends on the problem. It depends on the gaps.
Okay, so there is no minimal number that work.
No,
Okay.
you cannot, without further knowledge, you cannot say, but it depends on the gaps. And the way to do this is to monitor the convergence of eigenvalues and also residuals. And then you'll just see when you're converged and you have it.
Okay, thanks.
Yeah. Okay, so here I will use the matrix A because Arnoldi works also for non-Hermitian matrices, and then it's maybe not good to write down the Hamiltonian, which we typically think of a Hermitian matrix. So we have a matrix A, and for now we say we only have a matrix vector product A times V yields a new vector W. So the procedure works in the following way. The first step is, as always, we initialize first vector V1 by a random vector, and we normalize V1 by the norm. Okay, so this was as in the power iteration. The second step is, so this is a normalized start vector. The second thing we are doing is we have a loop for j equals 1 to m. So m is our maximal size of the Krylov space where we want to stop. So this is the Krylov dimension. And we will first apply our matrix A to Vj. So that's the present vector that we have in memory. We apply A, and this is a new vector W. Then we have to make sure that this new vector gets orthogonalized to all previous vectors. So there's a new loop for I equals 1 until j. We orthogonalize, so we first calculate the inner product of W with all previous vectors Vi. Then we subtract the component, so this is really modified Gram-Schmidt, minus Hij Vi. And so this is a loop. And then we calculate the norm of this vector, Hj plus 1, comma j. This is the norm of the new vector W, which is already orthogonal to all previous vectors. And finally, we store the normalized W in our next vector. So this is W divided by the norm, which we previously calculated. All right, so you see a few simple steps that we maybe number them. So we have A, B, C, D. And maybe just for completeness, let me tell you again. So here we apply A. So this is the step where we increase the Krylov space by applying one more bar of A that we apply. This is the overlap with previous vectors. This is orthogonalization. And here we normalize. Well, it's actually the two steps. Now, interestingly, so you notice here that of which seemingly seems like a matrix notation, and this is intentional because what we get now is we get the vectors Vj, which are really the columns of our V matrix, and those are the orthonormal basis vectors of the Krylov space. So Vj are O and B of Km psi 0 H, A. So that's what we wanted. But in addition, we also get the matrix Hij, which here, just because we don't want to confuse it with a Hamiltonian matrix, I will call R. Rij is Hij, which, due to the fact that this loop here ends at J, and we just go one more element, one more line down, has the following form. So in the first iteration, we get the diagonal element. So this is for the case here that I equals J. Both are 1, so this is H11. And we get in this step C, we get one more, the one line down, Hj plus 1 J. So this looks, the first row looks like this, and the rest of this matrix is 0. In the second iteration, we get two elements in the second column and one more below the diagonal. In total, this matrix looks like this, that it has a triangular shape, and it has one more row below the diagonal, and this is called upper Hessenberg form. And you can show that this matrix is the projection of of A into our Krylov space orthonormal basis. So this R matrix is what we need, V dagger A V. So you see that we have in one shot obtained iteratively by adding one vector at a time, not only an orthonormal basis of the Krylov space, but also already the projected matrix in the Krylov space. Now, and then we can diagonalize R. So this is really the Rayleigh quotient matrix. And a nice thing is that we get, in some sense, a special basis, a special orthonormal basis of the Krylov space, because if you just take the vectors and create any normal basis, then the R matrix will be dense, completely filled. But the special basis that we get makes it this special form upper Hessenberg. So let me now just briefly, because of time, I don't go into deep detail for the Lanczos case, but just give you some hints how this works. So if A is Hermitian, then we know, of course, A dagger equals A, and also means that R dagger equals R. And now if you look at an upper Hessenberg matrix, which is also Hermitian, then you immediately see that this has to be a tridiagonal matrix. So then R in this case will look like this. So you see, in the Lanczos case, the matrix is much simpler. And this means that B is reduced to just one element. So you see, this loop here in the Lanczos case is reduced in the Hermitian case. And you can, if you want, think about why this happens, and you can see that automatically in the Lanczos case, at least in exact arithmetics, the new vectors will already be orthogonal to the first few, and you only have to orthogonalize to the previous vector. And this is why this loop reduces to the simple form. So this means that the Lanczos case is much cheaper computationally, because you have the inner loop is reduced, basically drops. And you also get, of course, that Hj j plus 1 is the same as Hj plus 1 j star. This is just from Hermitianity. So you see that the Lanczos case is simpler. And perhaps I'll put the exact algorithm in the tutorial, because they are in all the cases, of course, more general. Now there's another important thing that we should point out, and this we will need for the time evolution part. There is a specific expression if we look at the matrix V of different sizes. So if we look at first at the expression, just give me a second. So if we are after the expression A, we can write down the vector W is A times Vj minus all components I equals 1 to j Hij Vj Vi. Sorry. So this is just what the algorithm does. It subtracts all the components along these the previous vectors, and then Vj plus 1 is the normalized vector, j plus 1 j. So if we combine this, then we have Hj plus 1 j times Vj plus 1 is equal to A times Vj minus Hij Vi, I equals 1, 2. Therefore, if we just change Avj to the left-hand side, we get sum over I equals 1 to j plus 1 Hij Vj, j equals 1 to m. All right, so you'll see in a second why I'm doing this. Let me now write this in matrix form. So if we do for all j, right, we can use this equation for all j. So I can write this as a big matrix vector, matrix product. So I just put V1 here, V2 here, until Vm minus 1. And then I'll put Vm in the last column. And on the right-hand side, I'll use this part here. So I'll have V1, V2, V1 up to Vm minus 1. And you see that the sum here runs to j plus 1. So I have to extend here one more column, m and Vm plus 1. And this is on the right hand side given by Rm, which is the m by m block. And we have to pad here one more row, hm plus 1m. Okay, so why am I doing this? Well, we can now, so you can work this through. I don't have time to go through this in full detail, but there's an important equation which we will get. If we work this out and we write this in blocks, so this is the matrix Vm of m basis vectors of the orthonormal basis. So consequently, this is also, so the total thing is the Vm. And this is Vm expanded by one more column. So this is a block matrix. If we write this separately, we get A times the big matrix Vm is equal to Vm times Rm. So this is the m by m block of the R matrix, plus Vm plus 1. That's the next column vector, times 0, 0, 0, so a vector which has zeros everywhere, and hm plus 1, comma m here. And this we will write as Vm plus 1 times the unit vector, the mth unit vector, which has zeros and 1 in the mth component, times the scalar m plus 1, comma m. And this is called a partial Hessenberg reduction. And this will be a crucial equation to understand the time evolution, Lanczos time evolution. So this is partial Hessenberg. And just as a comment, this kind of equation, you can write down the same thing, of course, for the Lanczos case, is also useful for a very cheap way of calculating the residuals of the approximate eigenpairs. And this can be exploited if you want to get some cheap estimate of the efficiency of the method. All right, so now we have in principle a very nice algorithm. But if you run this, if you carry this out in practice, then there's still some problems, and I just want to mention them. So the first problem which arises is that there will always be round-off errors. So if you have finite precision arithmetics always on computers, and therefore you get round-off errors. And the most problematic thing which they generate is that you get a gradual loss of orthogonality. So what does this mean? Well, we have devised the algorithm such that it automatically gets an orthonormal basis of the Krylov space, but this is only if we have exact arithmetics. If we have approximate arithmetics, we will see that this doesn't work, and after some number of steps, we will automatically get non-orthogonal vectors. And there's one cure to this, which is called explicit reorthogonalization, which basically means that instead of relying on the orthogonality which is built in, we will just have to go through all previous vectors and orthogonalize. And the other thing that we can do is so-called restarting. So if you imagine you start with a random vector and you want to, let's say you want to know the ground state. Then you run the Lanczos algorithm for 20 steps. And after 20 steps, you will get some approximation of the ground state. And instead of continuing, you can now just restart Lanczos from this approximate ground state, and starting from that, you will get a much better convergence. So if you do this, this can help. And there are more sophisticated ways of restarting. Some are called implicit. So what I'm saying is explicit restarting, but some more sophisticated ways are called implicit restart. I don't want to dwell too much on these details. The essential message I want to convey here is that there's a whole art of making this work on finite precision arithmetics. And the message is, don't implement this yourself. Use a library. And the reason is really that there are so many things that can go wrong, and there's a lot of sophisticated improvements over what I've said, which help making this stable. Another thing which is often used is so-called deflation, which is a method which removes parts of the Krylov space which are already converged. So imagine you run your Lanczos algorithm and you have already the ground state is converged, but you're actually also then converging the second largest eigenvalue. So you might have to continue this, but because the ground state is already converged, you can actually remove this. So you subtract the projector to the ground state from the Hamiltonian, and then this new thing has a new ground state, which is the state you want. These deflation techniques are also often built into sophisticated libraries, and therefore these things are quite complicated to get right. So don't do this yourself. The idea of this lecture is more to give you an idea of what are the central ingredients and how does this work in general, not so much of enabling you to implement this in a foolproof way. All right, so now, yes, please. Is there a question?
Drive, please.
Yeah. Hi. Yeah, I have a question about the stability.
Yeah.
And the interplay with symmetry. If you have an initial state which is in a particular symmetry sector, can you rely on this method to stay within this symmetry sector, or will the round of error slowly take you out of this sector?
If you have symmetries, it's always advisable to reduce to the symmetry blocks anyways, because this will reduce the matrix sizes a lot and also the sizes of the vectors. So this will improve the performance significantly. I'm not sure I can comment. So if you don't reduce the symmetries, which is suboptimal, I don't actually know how reliable it would be. I think it's just much better to reduce the minimal symmetries first.
Okay, I was just wondering, in the case of highly non-trivial symmetry, that might be complicated to resolve, but
sure. I mean, in this case, it's always easy to check, right? So I mean, you can always check that in which sector your resulting vector is.
Yep.
Yeah.
Okay. Thank
right.
you.
Okay, so just to move on, I want to now conclude this topic and basically conclude that we have now a method which gives us reliable access to the eigenpairs at the edge of the spectrum of large matrices, which can be either Hermitian, then we use the Lanczos technique, or they are non-Hermitian, then we use the Arnoldi technique. But now, in order to study MBL, we realize that we are not interested in the edge of the spectrum. We are interested in the center of the spectrum. And this problem I want to address now. Center of the spectrum. And in order to make progress here, one can use so-called spectral transforms or spectral transformations. What we have to do is we have to somehow bring the interesting part of the spectrum to the edge. So what we have is we have a spectrum like this. And what we actually want is a part here. Inside the spectrum. And directly, there is no way you can get this converged due to also the problem that we discussed yesterday already, that the convergence for eigenpairs which have small gaps, which is typically the case in many body systems. So in fact, I should draw this much differently. So I should draw a much denser spectrum in the part of interest. Small gaps are really a problem for the convergence of these Krylov space techniques. Typically in finite size systems, we have a maximal and a minimal energy. And now what we can do are certain transformations. So the simplest idea that one can come up with is called spectral fold, where you basically just say, okay, I'll take the Hamiltonian, I'll subtract some number on the diagonal, and then I'll take the square. So now if you take the number to be here, then you see immediately that sigma gets pushed down to 0. And if you square this, then the whole spectrum gets folded up to the positive part. So your new spectrum would look like this, that you have the interesting eigenvalues here, and then all the rest is up here. So this would be 0. So this is nice. It brings the interesting part to the edge of the spectrum, but it has the big problem that you have extremely small gaps close to the states of interest, right? So in practice, it turns out that this spectral fold transformation does not converge. So if you use the Lanczos algorithm for this matrix, this new matrix, this does not converge, unfortunately. So it's not extremely useful, but it gives you a hint how one can work with this. Now, the most successful and most powerful transformation that you can use is the so-called shift and invert transformation, which really takes a radical approach by saying, okay, we will take the Hamiltonian, we will subtract the target, and then we will invert this matrix, right? So what this does is, I can show you just a figure maybe to illustrate this. What this does is it, if you plot the original spectrum here, so we have the smallest energy and the largest energy here, and you plot the transformed spectrum here, and here is our target sigma, then you see that the transformed values have extremely large absolute values close to the target, and everything else is extremely small, right? So this has exactly the right properties. It has large gaps. It has a large separation of the absolute value of the interesting part of the spectrum, and the non-interesting part of the spectrum is basically pushed down to 0. So this is perfect. And the convergence of the Lanczos algorithm for this transformation, shift invert transformation, is extremely good. And I'll give you a very simple Lanczos code, and I'll let you play with the shift invert transformation so you can see how well this converges. Now, okay, so this is nice, but of course there's a big problem, because there's an excellent convergence of Lanczos. But we have a matrix inversion here. And this is, of course, a problem, because we want to work with sparse matrices here. And typically, if you just invert a sparse matrix, you cannot hope it to be very sparse. Luckily, this problem can still be solved for sufficiently large sizes that one can make real progress with this. So the first thing to realize is that, of course, we don't calculate this matrix inversion. Instead, what we do is we take the matrix H minus sigma. This is a sparse matrix. And then we calculate an LU decomposition using the Gauss algorithm. L and U are such that you have a lower triangular matrix and U is an upper triangular matrix. And you can then use this to solve the linear problem. So what you then have to do is you want to solve H minus sigma identity applied to some wave function is a new wave function psi tilde. Sorry, the inverse matrix. So if we write this the other way around, then what we have to solve is H minus sigma identity applied to the new vector is the old vector. So this is just a linear problem, and we can write this as LU psi tilde, and we solve for psi tilde.
David, there is
Yes.
a quick question by Kemal. Do you have zero modes in the shift invert method?
By zero mode, you mean what? That you get a zero eigenvalue?
I mean zero eigenvalues that don't allow you to invert matrix.
Well, so first of all, you don't invert the matrix, and secondly, numerically you never find. So your worry is that the target hits exactly a zero eigenvalue, right? So if the target is a zero eigenvalue, then this matrix here has rank deficiency of 1. Numerically, you never hit a zero eigenvalue. It's just because, you know, those are real numbers and the probability to hit exactly 0 is basically 0. So I think in practice, it's not a problem. You might get some extremely large eigenvalue numerically of H minus sigma to the -1, but that only helps for the convergence of. There are some cases where you can have exact zero eigenvalue. And in this case, it's sometimes not good to hit numerically this exact eigenvalue, because then, of course, if there's an exact 0, then you will indeed get the rank deficient matrix. In this case, one has to shift the target slightly to be off this special point. So in principle, yes, it can be a problem, which can be solved by just shifting sigma a little bit. But in practice, for the Hamiltonian case, we looked into this and we never faced any problem with this. All right, so now we still have to solve this LU decomposition, but it turns out that this is much faster than the full eigenvalue problem. Then, for example, these SY. So this in LAPACK, this function is called ZGETRF, sorry, for the LU decomposition, and for solving it's called ZGETRS. So this is really much faster than solving the eigenvalue problem, and there are massively parallel implementations for the LU decomposition, which you to use this on supercomputers. Massively parallel. Sorry, I'm writing wrong here. One is called Strumpak, and the other is called MUMPS. And with this, you can actually do really large system sizes of D from 2 times 10 to the 6 to 10 to the 7. If you want to read about the technical things, I give you a reference to where we wrote this up in SciPost Physics. This is 5045. That was 2018. All right. So the problem of shift invert is the following. You take the Hamiltonian, you subtract some target energy, and you calculate an LU decomposition. So that's the hard part. Once you have the LU decomposition, you can really apply essentially the inverse matrix by solving this linear problem, and this is fast. So once you have the LU decomposition, you can actually just apply the Lanczos algorithm by replacing the matrix vector product by the solution of the linear problem. And I'll give you this problem for the exercise. Write a simple Python code so you can see how this works. And this is extremely efficient way of getting internal eigenpairs. The only problem which this has is that the memory that you need to store the LU decomposition can be huge. So if the biggest problem that we have is H is sparse, much memory to store this, but L and U are much denser. They can still be to some extent sparse, but much denser. So we need a large amount of memory. So this is to be kept in mind. But using these massively parallel approaches, this can be remedied by distributing the memory over many computers, so that we can still solve extremely large problems with Hilbert space dimensions close to 10 to the 7. So this is still an extremely powerful method. I want to point out that this can also be used for the Floquet problem. And this is maybe slightly less known. So what you have in the Floquet problem, and there we can just a little bit more in detail. So we know that the eigenvalues of the Floquet problem are on the unit circle. Okay, now I have problems drawing a circle. So you can imagine that what I want to draw is a circle. So we have the eigenvalues on the unit circle. And now we can choose a target. And in order to avoid, here it's easy to avoid hitting any eigenvalue by just going slightly outside the unit circle and saying sigma is 1 plus epsilon. And epsilon is some small number. And now you can actually, again, use the unitary minus sigma times identity to the power -1. This is now non-Hermitian. And therefore, you have to use the Arnoldi algorithm. But you can, again, use a LU decomposition of L minus sigma and do exactly the same technique. The nice thing about this is that because the general complex eigenvalue problem is so much more expensive compared to the Hermitian one or to this real symmetric one, that this shift invert for Floquet systems is actually extremely efficient and works quite well. Again, here, of course, you need the memory, but you can go to larger sizes with shift invert also for Floquet systems compared to full diagonalization. All right, so this is one way of solving this problem. And I want to point out a second way, which is not shift invert, but uses a more general class of spectral transformations, and this is called polynomial filtering. Polynomial filtering. And this comes back to this spectral fold idea, if you want. This is, I should mention maybe that, of course, shift invert is an old technique, which was not used previously in many body systems, but now I think is established as a standard. And the same holds for polynomial filtering. It's also well known in numerical mathematics, but was also not very popular in many body physics until very recently. So the idea here is that we can ask ourselves, okay, if we know how to apply the Hamiltonian to a vector, what can we do? What are transformations which are realistic? And as we've seen in the discussion of shift invert is really at the edge of being feasible because it's an extremely hard problem to solve the LU decomposition, and is limited by memory. So in order to get rid of the memory restriction, we realized that if we can do h psi to some new vector, then we can actually calculate any polynomial of the Hamiltonian. So we can actually do Pm of h applied to psi, this psi tilde. And Pm is really a polynomial of degree m. So this is just k equals 0 to m h to power m ak h to power k applied. Yeah, okay, so that's the polynomial. And you can see that if I can apply powers of h to a vector, I can also calculate the action of the polynomial on a vector. Now, the main art here is to find suitable polynomials. So what we really want is we need a polynomial which maximizes the modulus of lambda in so maximizes modulus of lambda in the target space and minimizes the modulus of lambda outside. This problem is a well-known problem in numerical mathematics, and it is known that the best possible polynomials which solve this constraint here are Chebyshev polynomials. And this idea was used recently in the context of MBL in this very nice paper by Piotr Stjeran and Maciej Lewenstein and Kuba Szakrzewski. Which is now PRL 125.156.601 2020. And what they did is basically they expand a delta function centered at the target energy in terms of Chebyshev polynomials. I don't want to give the exact expressions here. You can look them up in this PRL, but I'll show you a plot so you can see how this works in Chebyshev polynomials. And this is really known to be the optimal expansion in this kind of problems. Okay, so this is just an example that I forgot to show. So this is what you can get if you use shift invert diagonalization. This is our paper on the many-body mobility edge, which really resulted from shift invert diagonalization. So if you look again at the shift invert spectral transformation, this is what we already discussed. And now here in comparison is the Chebyshev polynomial expansion of a delta function centered here at the target. And what you can see is that, so here the x-axis is the original spectrum scaled such that it's between -1 and 1. And the y-axis is the transformed spectrum with this p0 of epsilon transformation. And this is really in terms of Chebyshev polynomials. And what you can see is that this transformation indeed achieves nicely the goal, namely the eigenvalues in this interval here will be transformed to be values with a large absolute value, and everything outside will have small absolute value. So you get some separation of the subspaces, and using the Lanczos algorithm for this polynomial then gives you quite good convergence towards the target target eigenvalues. The problem is that you need very high orders of the polynomial. So Piotr told me that for doing L equals 24, he was using something like M equals 10,000. So this is quite high order of the polynomial, which is clear because you need to somehow fight the exponentially dense spectrum that you have. But the advantage is that you have a low memory footprint because you have no extra storage. You only need to be able to apply H, and you have to do this patiently for high orders to apply it to any vector, and then the Lanczos beautifully converges.
David?
Yes.
Maybe if you can come back to the plot before.
Yes.
There is a comment which says that for the Chebyshev polynomial expansion, the gap between the gap of the transform spectrum doesn't look very large. So
it doesn't look large, but it's much larger than the
original one.
The original one, because it's exponentially dense. And really the trade-off here is that you have to use an exponential, a polynomial which is exponentially large in system size. So of course you have to pay the price, right? Of course, there's no free lunch here, but the advantage is you don't need such a large memory footprint, and the price is you have to go to very high order of the polynomial. And of course, you have to monitor the precision of the eigenvectors that you get. So
that means to the expansion, M has to double each time you add one side.
Yes, correct.
Okay.
Right. But as Piotr showed very nicely in his paper, these gaps are sufficient to get convergence. At the moment, I would say if you look at massively parallel implementations, the quality of shift and also the performance of shift invert and polynomial filtering for this problem is comparable. Just because, if you have a massively parallel implementation, you already have enough memory because you use enough computers, so you have the memory and you can afford doing the LU decomposition. And once you have shift invert, the convergence is of course much better, the convergence of Lanczos. Nevertheless, if you don't have enough memory, and we will see this in a second, then this polynomial filtering is a very interesting and important alternative. So one should always consider both options and see what is best for the job. Right. So I got quite excited about this polynomial filtering when thinking about Floquet systems, because for Floquet systems, this huge memory, and there's not so much sense in doing parallel LU decompositions just because of the problem that the unitary is dense. So U is dense, and then we have to do something about this. So the first thing that one can realize is that in many local systems, even though we can still write a fast matrix vector product. So we can still find in many systems fast way of calculating U times psi. An example is the kicked easing model, which I mentioned in the beginning. So in the kicked easing model, you have hz equals sum I sigma I plus 1 z plus hi sigma I z, and hx is just a sum over all sigma I x. And the kicked easing, one way of writing the kicked easing unitary is e to the minus I t1 hz, e to the minus I t1 t2 hx, and t is the sum of t1 and t2. Now, this matrix is a dense matrix. However, we realize that this matrix here is diagonal. So this matrix is easy to calculate. And we also realize that this matrix, because all terms in hx commute, can be written as the product over all sides, e to the minus I t2 sigma I x. And now the problem is not so bad, because each of these terms we can easily calculate, because this is nothing but identity cross identity. These are all 2 by 2 up to site I. So this is site I. Then we have actually the exponential of sigma x. So this is e to the minus I t2 sigma x. And then we have identity cross identity. So we can actually, each of these terms we can calculate easily. It's a sparse matrix. Once we have them, we just apply them one by one. So we start in the last site, we apply to the vector, then we take the result, we apply the next site, and so on. So we have a series of sparse matrices, and then in the end, a diagonal matrix. So you see that even though U is dense, we can still work out a way of finding a fast matrix vector product without calculating U. And this is called a matrix-free technique. There are many ways of doing matrix-free multiplications, but this is one of them. So now that we know that we can have models where we can get a fast matrix vector product, then the next question is, can we do polynomial filtering? And because of the Floquet problem is a bit different, has a complex spectrum on the unit circle. So there are two ways of doing this. So we know the eigenvalues are on the unit circle, and in principle we can think about, as I mentioned previously, we can Hermitian part, which is U plus U dagger. Then we squeeze the spectrum to be on the real axis, and then we can use regular polynomial filtering. But it turns out there is a better way, much better way, which uses the fact that we have a complex spectrum. And so I studied this in some detail, and I tried to find the optimal polynomial, which has this property that it maximizes the absolute value of the polynomial in the target subspace, and it minimizes the absolute value outside the target subspace. I optimized this just naively numerically, and surprisingly, I found a very simple polynomial. So the best, according to me, so it's not a mathematical statement, it's just a numerical statement, but perhaps one of you can prove that this is the best one, as it can be proven for in the real case that the Chebyshev polynomials are best for the real case. So I'll write best in quotation marks, polynomial, to find the eigenpairs close to some target face. So let's call this phi target. And we really want all eigenpairs close to here, and we don't want the others. And the best polynomial turns out to be very simple. Gk of U is the sum over m equals 0 to k e to the minus I m phi target. So this term is trivial because it just rotates the target space such that it's at at 1. and then you have u to the n. That's it. So essentially, this is just the geometric sum, which has a closed form, which you can write down as 1 minus e to the I k plus 1 phi target u to the k plus 1 times 1 minus e to the minus I phi target u to the minus 1. And here you can see why this is so good, because, okay, this is of course some correction factor, but this part here is identical to the shift invert transformation. So you see that it contains some part which is shift invert, and of course this is something which doesn't go away, because for a spectrum which has modulus 1 for all eigenvalues, the geometric series does not converge. But still, this is true. And it turns out that if you look at this polynomial, that it does exactly what we need. So here is the original spectrum on the unit circle. And the interesting part is this red arc here, which is the target subspace of eigenvalues which I want. And now if I use a polynomial of order 30, then I see that this gets transformed by gk of u to a spectrum where the target arc is the red arc here, and everything which is not on the target is scaled down to this blue spirals. And you see that the separation of absolute values is quite good, and the eigenvalues are spread out on the complex plane as well. So there are also complex gaps which accelerate the convergence. So if you look at just the absolute value, you see that the target arc is this red part here. Most of it has a large absolute value for this part down here, which has the same absolute value as some parts of the spirals. So what you can now hope is that you get very good convergence of Krylov space methods for the part of the spectrum which is scaled up here. And this is indeed the case. And this is, roughly speaking, 80% of this apple-shaped arc will be well separated from the rest, and you get very good convergence.
David, we have a comment from Anton?
Yes.
Yeah, it seems to me that what you're proposing is basically a plain Fourier series on the unit circle. So it provides you an expansion of a delta function on the unit circle. So it's not much of a surprise that it's kind of a best approximation. I mean,
yes,
probably you can even might arrange it in a form of a proof. I don't know.
I'm sure you can prove that. Yes, I'm sure you can prove that.
So it's kind of a credible statement that it's really the best choice.
Right. Okay. I mean, for my purposes, my statement is just that it works, and that's enough, right? So.
Yep, sure.
One can calculate the size of the arc which gets to scale to the outer apple, and you can estimate that you need a size of the Krylov space, so number of column vectors.
Sorry, may I interrupt you? I also have a simple question.
Please.
The apple kind curve is periodic, apple form curve, and the original curve, original domain is not periodic. It's just linear. So the question is, which points are you identifying? Which points are you gluing?
Oh, this is just so the degree. So this polynomial just glues this part here, gets moved here, and this part here. So now it gets messy. Let me redraw. So this part here, this edge here of the target arc comes from above, and this part here comes from below. Right, and they touch indeed at I think at 1. Right? So it's just, I mean, if you just calculate the values of this polynomial using the unit circle as input, you get this mapping, and you can identify. It's easy to calculate, right? Because all these values on the unit circle are e to the I phi. Now you plug this into the polynomial, and you can identify where the points meet and so on. So you get multiple passages through 1 and I think through 0. But this is all not important really, because what you can actually get is you get converged parts of the spectrum basically here, because this inner part has already a similar modulus to the spiral, so this part doesn't converge well.
We have another question by Artem, please, Artem.
Mm-hmm.
Yes. So my question is not directly at the method, but rather in general. It's not quite clear to me why for Floquet system you would even want to target a specific value, because I mean there's no energy density that you could target, right? Also, if you had uniform level spacing, you cannot really compute a level spacing. So like,
why is that?
Well, I mean, if I guess for many interesting Floquet system, the level spacing is uniform, right? So it's kind of
no, this is not correct. It's not correct. What you probably mean is the density of states is uniform, but the level spacing statistics follows in most cases except MBL random matrix theory, which you might want to test. So this is one reason why you might want to find, let's say, 100 eigenvalues close to this target. Then you can test level spacing statistics.
Yes, okay, that I can
Another thing to test is ETH. So you might want to get eigenvectors close to the target, and then you can test ETH. And for example, studying MBL transitions, this is an interesting thing to do.
Okay, I see. Thanks.
And of course, you might want to consider several targets, but in Floquet systems, all targets are the same because of what you said. So it doesn't really matter which target you want to you will address. Okay. Good. So just to finish this part, I want to conclude that you can use the Arnoldi algorithm using directly GK of U, and then you can actually solve exact eigenpairs of Floquet unitaries with dimension larger than 1 million, which I think cannot be done in any other way. So I'll just give you the reference. If you're interested, this is on archive 2102-05054. All right, so with this, I want to conclude that we have now seen that we can use either shift invert or polynomial spectral transformations to move the interesting part of the spectrum from the center to the edge. And once we have done this, we can use either the Arnoldi or Lanczos algorithm to calculate exact pairs. And maybe one thing I forgot to say, but this is of course crucial, is that the eigenvectors of the transformed matrices are identical with the eigenvectors of the matrix themselves. Therefore, it's easy to calculate from the eigenvectors directly the eigenvalues, but you can also, of course, use the inverse transformation to calculate the eigenvalues. So this concludes this part, and I want to use the last few minutes of this lecture to discuss a different topic, which also makes use of Kirchhoff space techniques. And this is the question, how to calculate real-time dynamics. So now we switch gears completely, and we try to make contact to experiments. So in experiments, of course, you know that you cannot measure eigenstates, you cannot measure eigenvalues, and let alone in the center of the spectrum. But what you can do is you can measure the real-time evolution of observables. And these are called quench experiments, for example. Evolution of observables. So what we really want is we take some initial state and we look at the evolution of local observables, observable. And in order to do this, the easiest way to do is take the initial state and calculate the time evolution of the initial state, so that we just have to measure the observable in this new time-dependent state. So this is e to the iht O e to the minus iht psi 0. O is a local operator, so this is typically a sparse matrix, so it's easy to calculate the product of the times any wave function. And our main interest here is how to calculate the exponential applied to the wave function. For small systems, we can, of course, resort to full diagonalization. Which really means that we solve the eigenvalue problem HV equals D times V, where D is the, I did this already in the last lecture, so it's just a repetition. The eigenvalues on the diagonal, and V is the matrix of eigenvectors as columns of D-dimensional Hilbert space. And then it's easy to calculate e to the iht by just noticing that we go to the eigenbases and then we have a diagonal matrix exponential, which is easy to calculate. All right, so you all know this, but now, of course, again, the question is, how can we do large systems? And it might seem at first that you need all eigenvalues to get the exact dynamics. And of course, if you think about using launchers to calculate the eigenvalues, you need to scan the spectrum with many shifts to do your shift invert. So this is not practical. Luckily, there is a better way, which only needs, again, a fast matrix vector product. Psi tilde from h times psi. Sorry, h times psi. For example, we can get this by storing h as a CSR matrix. So the first thing you can do is you can try to use just a direct Taylor expansion of the exponential, right? Because typically what we do is we want the time dependence on a grid of times. And we might be able to choose a small time step. So then it makes sense to do Taylor expansion. So we can try this and we can write down psi of t is e to the I minus iht applied on the initial state. And then you can write this down formally. And this works because the convergence radius of the exponential series is infinity. It works I have to say in exact arithmetics, h to power k applied to psi 0. And of course, you can approximate this by truncating at k max, and you get some result. Now, this is nice and easy and only employs matrix vector products. But the problem is, of course, that this is in fact known to be numerically unstable. So there's for example, a nice discussion of this unstable in Muller and van Loon 2003 in a paper called 19 dubious ways of calculating the matrix exponential. And there they show examples which are quite shocking, which yield completely wrong results, just due to the fact that the numerical precision of doing this is not sufficient. However, we can make progress from this simple Taylor expansion by a first observation, which is that if we look at this expression, we realize immediately that the vector that we get here is a member of a Krylov space. So this is indeed inside the Krylov space of dimension k max, spanned by H applied on the initial state psi 0. And here, crucially, you have to use a different kind of Krylov space from what we've had before, because here we have to work with the initial state. And this is extremely important. So previously, it doesn't really matter which initial state we had, as long as it had enough overlap with the eigenstates of interest of your system. But in this case, we have to use a physical Krylov space, which is spanned by the initial state, and this is good. And it was realized that, in fact, the way to make this numerically stable is by using, again, an orthonormal basis of the Krylov space. So instead of directly using the vectors of the Krylov space generated by the exponential series, we use an orthonormal basis of the Krylov space of H psi 0. And we can use this to make progress. Now, another question is, of course, what happens if we want to do a large time step? Obviously, using this kind of Taylor expansion, you realize immediately that it's advantageous to use small time steps, because then the series is supposed to converge quickly and you don't have much problems. And in fact, for very small time steps, it might even be numerically feasible to just directly do the Taylor expansion. If you have a large time step, you can solve this easily. If this is time and you want to go to this time here, by introducing intermediate time steps. So you break this up into delta t, 2 delta t, 3 delta t, and so on. Now, to go from 0 to delta t, you just use the Krylov space H psi 0, as I've written above. And now, the next time step, you use a different Krylov space. You use the Krylov spanned by the previous time step. So instead of psi of 0, you use psi of delta t. And this way, you have essentially a rotating frame, which is always optimized for the next time step. And this way, you don't have any convergence issues. Now, how do we get the orthonormal basis of the Krylov space, and how do we use this? Well, as before, we use the Lanczos or Arnoldi algorithm, or Arnoldi on kind of problem, typically Lanczos if we have a Hermitian Hamiltonian, and we will run m steps of the Lanczos algorithm, starting from psi 0. And then we come back to the equation that we derived, that after m steps, they call this n, sorry. After n steps, we get a partial Hessenberg reduction of the form HVN equals VN Rn. Rn is the Rayleigh quotient matrix, and Vn is the matrix of Lanczos vectors, plus the extra term for the next iteration, Vn plus 1 times Hn plus 1. So this is a number. This is the matrix element, the lowest one in the next column. And the unit vector, the nth vector transposed. So this here is an outer product. All right. So if we do this, we can work this out exactly. And this is the last thing I want to do here. So please bear with me for a few more minutes. So the initial state is the vector v1. And our problem is really to solve e to the minus I t h applied to the vector v1. And we can write this formally as e to the minus I t h times the matrix of Lanczos vectors times E0. So that's the 0th unit vector, which is really just 1, 0, 0, 0, 0. So if you apply E0 to the matrix of Lanczos vectors, you get, of course, the first Lanczos vector, and the first Lanczos vector is V1, right? So this is nothing but a formal rewrite of this thing. Now, in the next step, I will use formally, so of course not numerically, but formally to show that this works, a Taylor expansion of the matrix exponential. So I get k equals 0 to infinity minus it k power k by k factorial h power k vn e0. In the next step, I will split the sum. I will separate out the first term, which is nothing. So k equals 0 is nothing but vn times e0. This is nothing but the initial state, okay? And then we get the correction, sum k equals 1 until infinity minus it to power k by k factorial h to power k minus 1 times h. So I split h to power k. K starts at 1, so that's fine, into one factor of k to the right and the rest to the left. And then I write what I had before, vn times e0. And now I want to insert here my partial Hessenberg reduction. So this is nothing but Vn times the Rn matrix plus Vn plus 1 Hn plus 1 comma n En transposed. And you see that I multiply everything by E0. So maybe let me just copy this down here. So we have E0 and we have E0 here. Now, immediately you can see that if n is larger than 0, which of course is the case here, if n is large enough, these vectors are perpendicular. So this part here is 0. This means that this extra correction term drops out. And just in order to not take too long here, I will skip the steps. So I can do this kind of separation of one Hamiltonian factor and one term I can factor out always, because now I have h to k minus 1. If k starts at 1, I have gotten rid of one more power of Hamiltonian, so I get one more factor which I can pull out. So I can repeat this for n steps, and for n steps I will see that the extra term always drops out until I reach size of the Krudov space, in which case this no longer drops out. So after n steps of this kind of reduction, I get Vn times k equals 0 until n minus it power k by k factorial Rnk power k e0. So this is the terms I pulled out to the left, plus sum of the rest, which is k equals m. Now I have this should be, sorry, this should be an n to infinity minus it power k by k factorial, and then h to the power k minus m. And here I have the rest. So this is Vn Rn power n. Okay, sorry, I confused n and m here, but I just want to give you the idea of what happens here. E0 plus the term, which the correction term, Vn plus 1 times Hn plus 1. So this is again from the partial Hessenberg reduction. En transposed Rn power n E0. And what you can see here is Rn is an upper Hessenberg matrix. So if I apply powers of it to E0, each power, so E0 is initially a vector which has a 1 in the first component and zeros elsewhere. If I apply one power of Rn, it will fill in one more component. So after applying one power, I get two components which are filled in. If I apply another power, it will fill in one more component. So each power will drop the limit of non-zero matrix elements, and we will, in each iteration of our procedure, we will fill in this vector. And you can see that as long as the last component remains zero, the overlap with En transpose is zero. So as long as this n here is smaller than the Krylov space dimension, this extra term will drop out, and we can continue factoring out the parts to the left. And only when this last component here hits the last entry, which means that the power we have here is n, which is the size of the Krylov space, this thing stops, and we cannot no longer get rid of this term. This means that in total we get something like Vn sum over k equals 0 to n minus it power k by k factorial Rn power k applied to the initial state, plus an error of the scaling, dominant scaling t to power n by n factorial times something like the norm of the Hamiltonian to power n. And you can see that if I use a large enough Krylov space, then because of this n factorial, which is a huge number, for short enough time step t, this error will become always negligible, right? So I can always choose my Krylov space large enough such that the error I'm doing by truncating here is actually negligible. And that's why I can get numerically exact results for the real-time dynamics using this technique. So what have we gained? Well, you see that we now have only powers of the Rayleigh coefficient, Rayleigh quotient matrix, Rn, which is a much smaller matrix. So if we re-exponentiate, so this is approximately, if we have convergence, something like Vn times e to the minus it Rn times E0. This really is a small matrix exponential, so this is easy to calculate. Vn is the matrix of Lanczos vectors, so this is a big rectangular matrix, d by n. This is n by n. And this is the initial state in the basis of Lanczos vectors, so this is n, size n. So we can easily calculate this dense matrix exponential. We have the Lanczos vectors, so we can transform back to the initial basis, and this way we get an extremely powerful method to get the real-time dynamics. I want to conclude this discussion by just showing you what can be done with this. And I think one of the nice works that we did, nice because it's matches experiments extremely well, is the study of the imbalance decay in the XXC chain with random fields. So I'll just finish by telling you what the imbalance is. So this experiment works in the following way. You take a system which has interactions, hopping, and disorder, and you prepare an initial state, which is, for example, up, down, up, down, up, down, up, down. This is, of course, not an eigenstate of the Hamiltonian. And now you ask, how does this ordering pattern decay as a function of time? So you calculate really time dependence of this wave function and measure an observable, which is called the imbalance, which is something like sum over all sides minus I to power I as I, which measures all. So initially on the even sublattice you had up, and on the odd sublattice you had down. So you're measuring this as the maximal imbalance, and if you have a more homogeneous distribution of magnetization density, then this imbalance would be zero. And then you can calculate the time evolution of the wave function and measure this observable by calculating psi of t I psi of t with this Krylov space time evolution. And what you can see is that at weak disorder, you get a very quick decay of the imbalance with some characteristic oscillations. And as you increase the disorder, this decay gets slower and slower. And if you're in the MBL phase, there is no decay at all. And this slow and varying decay was discussed in the context of slow dynamics close to the MBL transition, which is really a universal phenomenon in all MBL models. Yeah, this is something you can study with this real-time dynamics. And with this, I think I should conclude and want to just conclude by saying that we have seen that we can use Krylov space techniques to get exact eigenpairs, either at the edge of the spectrum or by using a spectral transform in the middle of the spectrum, which is important for MBL studies. This can be also done by using matrix-free techniques or sparse matrix techniques and can be scaled to quite large system sizes. And the other thing that we've seen is that you can look at the real-time dynamics of many-body wave functions using a special Krylov space, which is spanned by the initial state of your system, of your, let's say, quench protocol. And this is an extremely powerful method which you can use to study quite large systems. Just as a reference for the Heisenberg model, this can be scaled to system sizes beyond 30 spins without any problems. And maybe just as a final word, again, this is something which one probably should not implement on your own. There are very powerful methods, libraries, MPI-based libraries for this kind of techniques, which are called SLEP-C. And this comes in combination with PET-C. Someone wants to actually do this, please don't implement this yourself, use libraries. With this, I'm done and would be happy to take questions.
Okay, thank you very much, David. Okay, we have a first question by Anton, please. Anton.
Okay, thank you for such a wonderful lecture. I'm really impressed by these numerical capabilities. Yeah, I'd like you, it would be great if you gave some comment regarding how all of those methods perform in the case where the original matrix, let's say the Hamiltonian, is close to some nilpotent matrix. I mean, that has non-trivial normal Jordan form, meaning that it cannot be diagonalized, and then I can perturb it in a small way so it becomes diagonalizable, yet it's close to something that is not diagonal. And I wonder whether this is a complication for such a method, because the problem is close to something that is ill-conditioned or ill-formed, even ill-posed.
Right. Well, okay. I mean, I guess you are mostly interested in the eigenpair algorithms, right? Because for time evolution, I would suspect that there is no big problem.
Yeah, I think so. Primarily, it's about eigenpairs. I mean, how
but
they
for
are
eigenvalue problems, indeed. So if you have a non-diagonalizable matrix, you have less eigenvectors than the multiplicity of the eigenvalue, right? So I haven't tried to use the Arnoldi method in the case of a non-trivial Jordan block, but I would somehow expect that you should still get the eigenvector, or you should get the eigenspace, which is of course rank deficient. This suspicion comes from the observation that also if you try to do full diagonalization, you have the same problem, right? So you try to diagonalize numerically a non-diagonalizable matrix, and it turns out that normally you find the eigenvectors except one, and you also find the correct eigenvalues, and I'm not sure about the degeneracy. So you can try it, and I think you will get some limited information. Obviously, you cannot get the full information because you're, as you're saying, you're not solving the problem. But I can't. I don't have more to say than this speculation.
Yeah. I mean, I was wondering whether they like being in some way close to such situation. I mean, when you have a matrix with a proper diagonal form, but that is in some sense close to such a deficient matrix, yeah. Whether this is a complication.
Well,
looks like there is not much.
What happens close to what is called an exceptional point is that an exceptional point has the property that the two eigenvalues which coalesce at this exceptional point, they split in a fashion which is similar to a square root, a complex square root, right? So this means that the gap, if you go away from this exceptional point, the gap between these eigenvalues grows like a square root. So I guess if you're very close, then you will see a very small gap between these two eigenvalues, and probably numerically you cannot distinguish from zero. Other than that, well, it depends on how close you are in the end, right?
Okay.
Yeah.
Thank you.
Robin, please.
Hey, I have got a question, and I guess doesn't make a lot of sense. But can you use MPS states in Lanczos, or doesn't work due to the orthogonality of your matrix product states?
Well, so the problem with using MPS is basically you need to be sure that all have small entanglement, right? Because if at any point in your algorithm you encounter highly entangled vectors, then an MPS is not a good compression of this vector. And in this case, you will be back. You have no gain over using the full vectors. If you are, let's say, in the MBL phase, I would suspect that you can actually do this. Yeah. So there are some techniques called and so I think there's the other one is called SIMPS, shift invert MPS, which try to do exactly that. They try to use matrix product states as representations of all the vectors occurring in this kind of algorithms, and then they just build a Krylov space and use variant of the Lanczos technique. So in principle, you can do this. I suspect that this would work even better using polynomial filtering, just because it's much easier in the context of MPS. But you can only hope that this will work deeply in the MBL phase, because there all the vectors you get have low entanglement and can be well written in terms of MPS. So as a general method, I think this will not work because the MPS is not an efficient representation.
I have a question myself. David, so for the polynomially filtered technique, is there a difference? I mean, in the convergence, in the order of convergence of the polynomial, depending on which phase you are. If you are like deep in the MBL, where, for example, we know that eigenstates are not very far from exact product state in the spin basis. And if you start from such a state, I mean, do you need the same very large order in the polynomial as compared to, let's say, completely ergodic state?
I think so. Because the order of the polynomial is determined by the size of the window in energy that you want to address, or in the flow case, the arc on the unit circle. So the only thing which really comes into play is how much of the spectrum you want to get. And this determines the order of the polynomial, because you want to blow up the absolute value in this section and you want to minimize the other absolute values. The nature of eigenstates doesn't play a role at all here. And if you use a lower order, then you will not get will not get enough eigenvalues with a large modulus. So I think it's really the order will be the same. It is I also doubt that the convergence of the Lanczos or Arnoldi will be much different, but it's possible that some slight difference in the number of iterations you have to do, the number of applications of the polynomial on vectors. But I don't have much experience with this yet, so I can't comment more. But the order of the polynomial for sure has to be fixed just by the size of the window you want to get.
Okay, so this is still an exponentially growing system.
Yes, yes.
I see. Thank you. Other questions? No. Okay, maybe you can say if okay, a lot of participants they are left already for lunch probably.
I think I'll write in the Slack about the tutorial.
Yeah.
So the idea is I will unfortunately I'm not yet done, but shortly, and I will post a Jupyter notebook in the Slack channel, and then it's probably best to meet in the Gather town to discuss the notebook so that people can show me what they thought about, and perhaps I'll just have like a 30-minute Zoom to go through for everyone who's interested in a plenary session through the notebook. So there will be a part where we discuss individually on Gather. Let's say, so I think it's 1.5 hours, right?
Yeah.
So let's say 1 hour for individual discussions on Gather, and then half an hour in the end for a plenary discussion of the whole thing. And as I said, I'll post this the notebook in the channel today, and presumably because there's not so much time to work on this until the tutorial, I will also hang around and Gather later on, and also people can write in the channel in the Slack, discuss this later on in the week. So I think there's no immediate constraints on my side, and I'd be happy to discuss this also later in the week.
Okay, good. Yeah. So you do okay. So you give the instructions on
yes.
Slack. And on Gather, I don't know if you already visited the Gather space, but there is a big classroom, and so there is a special place where you can speak to everyone.
Right, I've seen that. Yeah.
So that can be convenient at sometimes to if you have something in general to say, because we cannot run Zoom and Gather in parallel. It will be a mess.
Sure. Yeah. No, that's right. Yeah.
All right. Good. Okay. So thank you again, David. That was a great lecture. Thanks.
Welcome.